Hello, and thanks for joining us for this quick overview of an 8-channel beamforming system using the Pentec Model 4207 I/O processor and the Model 7153 A/D software radio module. Beamforming is typically used with an array of sensors or antennas to improve receptivity in a specific direction, for example, from a single cell phone. The signal from a given source arrives at each antenna based on the distance between the source and the antenna, so the antenna signals have relative phase and amplitude offsets. Beamforming adjusts the gain and phase of each antenna signal to compensate for the different delays and signal paths to each antenna. These adjustments align the waveforms from each antenna for signals arriving from one particular direction. When the signals are summed together, the non-aligned signals arriving from other directions cancel each other out, while the signals from the beamformed direction add constructively for greatly improved signal-to-noise performance. So by electronically adjusting the gain and phase in each path, the antenna is effectively steered for directionality. Now let's look at the hardware we've chosen for this system. First, the Model 4207 I/O processor is a VME and VXS single-board computer with a dual-core MPC 8641 Freescale PowerPC processor located in the upper center of the block diagram. It features two PMC or XMC modules, one in the left and one in the right. In the center of the diagram, you see a gigabit serial crossbar switch, which is connected to the PowerPC, which controls all of the switch ports. It allows the crossbar switch to join any two switch ports together, providing an extremely flexible interconnection scheme for all of the major resources on the board. The crossbar switch is protocol transparent, so it can handle virtually any gigabit serial traffic. Both XMC modules have two 4x links going to the switch. In the lower right-hand corner, a Vertex 4 FPGA also has two 4x gigabit serial links connected to a Xilinx Aurora gigabit serial interface engine right inside the FPGA, implemented as an IP core. Now let's look at the mezzanine modules. The Model 7153 software radio module is a PMC and XMC mezzanine module. It features four 200 MHz 16-bit A/D converters, a timing, clock, and synchronization section, and two Vertex 5 FPGAs. Inside the larger FPGA, shown in the center, are four digital down converter IP cores, each capable of accepting A/D samples from any one of the four A/D converters through the use of multiplexers in front of each DDC. Each DDC has a decimation range of 2 to 256 in steps of 1 and can deliver down-converted baseband bandwidth signals from 625 kHz to 80 MHz. Each DDC also has programmable gain and phase shift controls accessible to the processor across the PCI-X interface. In this system, we will be assigning one A/D converter to each of the DDC channels. At the output of each DDC is a power meter that calculates the down-converted signal power. Each power meter is equipped with a threshold detector that generates a system interrupt if the output power exceeds the upper threshold or falls below the lower threshold. These features simplify gain calibration and signal monitoring tasks that otherwise would have to be done in software by the system processor. A summation block, also in the FPGA, adds the four DDC outputs together to perform the channel combining for beamforming. Finally, the module includes an Aurora gigabit serial interface engine that accepts a propagated sum on one 4x input port and delivers the new propagated sum out through a second 4x output port that includes the contributions from the four onboard channels. This diagram shows two Model 7153 PMC-XMC modules installed on the Model 4207 I/O processor board. At the top, we have a signal generator feeding a power splitter with 8 outputs connected to each of the 8 A to D inputs. Joining the two 7153 modules is a clock synchronization cable that synchronizes the DDCs and guarantees synchronous sampling across all 8 channels. Signals from the first 4 channels on the left module are summed in the left summation block, and signals from the second 4 channels on the right XMC module are summed in the right summation block. The summation output from the left XMC module is delivered using the 4x Aurora link into one port of the crossbar switch. Each red 4x link is capable of data rates up to 1.25 gigabytes per second. The left 4-channel sum is connected through the crossbar switch and delivered into the summation port of the right-hand XMC module. The Aurora summation from the left 4 channels is then combined with the right 4 channels and then delivered to the crossbar switch from the right summation output port. The 8-channel combined sum is then delivered through the crossbar switch into the Aurora engine on the Virtex 4 FPGA. The Aurora engine decodes the stream and delivers the data into a designated block in the DDR2 SDRAM attached to the FPGA. The PCIX interface inside the FPGA presents the SDRAM memory as a mapped resource appearing on processor bus 1. The PowerPC reads data from the FPGA DDR2 memory across the PCIX bus number 1. The PowerPC creates a beam-formed pattern display and presents it via its front panel gigabit Ethernet port to an attached PC for display. So here is our complete beamforming system with all signal paths shown. Notice how the crossbar switch makes it simple to set up exactly the right data interconnection paths we need. So how can we test the beamforming system? If we set all gain and phase adjustments on all 8 channels to be the same, we are effectively steering the antenna to an angle of arrival of 0 degrees, or directly perpendicular to the plane of the array. Now we need to move a signal source in front of the array so that its angle of arrival varies from plus and minus 90 degrees from the perpendicular. We'll now measure and plot the summation output of all 8 antennas as the source is moved in a semicircular arc of 180 degrees. Notice as the source is rotated, we're plotting the sum output as a function of the angle of arrival. Here you can see the source is rotating in the 180 degree arc in front of the array. This produces the classic beamforming pattern you see here in the lower left. Notice the maximum response is at an angle of 0 degrees. Moving the source in an arc is not always easy to accomplish in a lab during development, so we can simulate this movement using a very clever scheme. Instead of moving the signal source, we can use a stationary source and artificially introduce phase shifts in each channel to simulate the delay paths of a source moving throughout the 180-degree angle of arrival. The resulting graph is identical to the previous one, as you can see, but it's far easier to achieve the testing this way than with actually moving the source. And this is a classic way of testing and characterizing beamforming systems. Here we see the larger view of the simulated beamforming graph. For this plot, we used internally synthesized signal sources for the DDC inputs instead of the live A to D converters. This is an excellent way to validate the signal processing logic performed in the DDCs and summation blocks, as well as the signal propagation paths through the gigabit serial links, the crossbar switch, the FPGA memory, and the PowerPC. Now it's time to turn on the A to D converters and use live inputs. Here's the same pattern with live A to D inputs using the digitized analog signals coming from the 8-port splitter. Because input cables, transformers, and A to D converters all have slightly different characteristics, we've tweaked the gain and phase of each channel to match them. Although the matching was not perfect, you can still see the nulls are about 50 to 60 dB down instead of 100 dB with the synthesized ideal sources on the last slide. By the way, the built-in power meters on each channel made the gain calibration a lot easier. In this system, you can see the Model 4207 is a very versatile platform for the two 7153 PMC-XMC modules. Together, they provide 8 200 MHz 16-bit A to D converters, 8 digital down converters, built-in power meters, built-in summation blocks for beamforming, and Aurora I/O engines in both the 4207 and the 7153 to support the propagation of the sum. The flexible crossbar switch in the 4207 provides just the right interconnects to support the required signal flow paths. Everything we've presented here fits in a single VME slot, and most of the high-speed signal processing is already done in the FPGA hardware. If you need more than 8 channels, you can easily extend the Aurora summation daisy chain to any number of identical 8-channel subsystems by using the VXS backplane connections. Finally, these products are fully supported with Linux and VxWorks software tools. For more information about these products, please visit our website. And thanks for joining us today.